Hi, today we'll talk about chapter 2 in A2, which is gravitational fields. So how this video will work is that we'll just go through some equations and some past year questions, and that'll be about it. But if you have any more inquiries, questions, you could always leave some comments down and I'll try to answer them if I can. Alright? So before we begin, we'll just go through some important stuff that you should take note of. So first are the equations, as you can see here. Oops, let me fix this. This is F. So for the equations, right, we'll talk about 6 different equations, and for the definitions, there are 3 definitions that you should take note of, which is Newton's law of gravitation, gravitational field strength, and gravitational potential. Now for the definitions, I'll not provide you with the definitions because you should be able to find them online or in your textbook. Okay, so now we'll go through each of the equations and how they are derived to give you a better understanding of this chapter in general. So for the first one, we'll talk about gravitational force. Now, for gravitational force, we discovered that for gravitational force, the force is directly proportional to the inverse square distance, and it is also directly proportional to the product of masses. Of what masses? Technically, it can apply for any mass, but for this case, we should only consider large bodies of masses. Alright, so by knowing these two, we can combine them and we can yield this equation. And to remove the proportional symbol, we will introduce a constant of proportionality, and this is the gravitational constant. Alright, so it's really just like that. It's quite simple for this one. So for the next one we'll be talking about is the gravitational field strength. Now this is a different equation to describe the gravitational field strength. As we all know, we usually use it as F equals to mg, and we can just do some algebraic manipulation and we can get the gravitational field strength. Right. So the thing is that how we derive this new gravitational field strength is that we equate the gravitational force that we got previously with this equation. So this one is the first equation, and we equate it with this equation. So by doing this, we can just cancel out certain stuff. Oh, and do take note that for the gravitational force, right, the capital M here is actually for a more massive object, whereas the smaller m is given for the smaller object when you're doing your calculations. Alright, so by doing so, you will find that the gravitational field strength will look something like this. So some might wonder why only one body is involved, but you can see that it's only one body will be involved because, well, we're just talking about the gravitational field strength of one body. So the other body any other bodies of masses would probably not influence the gravitational field strength of that body. Yes. Right. So next we'll go on with the gravitational potential energy. So now for the gravitational potential energy, right, the concept is quite simple. If you look at it, it somewhat resembles the gravitational force, which is, I'll write that down here, Fg gmr over r squared. Now, the way that you might be able to string a connection between them is that you can use the work done concept. Now, if you remember from your previous physics lessons, work done is equal to force times distance. Correct? So force times distance. So notice that this equation somewhat resembles this one. The only difference is that the gravitational force has a square at the bottom, whereas the gravitational potential energy does not have a square. So you can somewhat draw a correlation between these two in the way that it seems as though the gravitational potential energy is the gravitational force times a distance, which is just r. As we all know, r represents the distance, correct? So you will get something like this, which is actually equivalent. Now, the only thing that most would be confused or curious about would be the negative symbol here. So why is it negative? Well, we use negative because we set the infinity as the 0 point. That is, we treat it as the reference point for our calculations, and that's why everything that is within it would be considered negative, as since everything is infinite, since we set infinity as the 0 point, something must go past infinity to even get a positive value. So basically everything that's within infinity would be negative. Alright, so the next one we'll talk about is gravitational potential. Well, gravitational potential is actually very similar to gravitational potential energy. The difference is that it is, if you look at the equation, you'll notice that there is a slight difference in the way that there's no mass here, there's no smaller body of mass here, but you can see that there's still an r here rather than an r square as compared to the gravitational force. So let me clear that out. Alright, so what does this mean? Well, if you're speaking from a definition perspective, the definition of the gravitational potential is just that it's just the gravitational potential energy per unit mass of at any point. So let me write that down. So it means that it is the gravitational potential energy per unit mass at any time. Oh, sorry, not time, point. Okay, so what this means is that imagine there is a body here, okay, a body of mass, and then like this is the gravitational field, right? You can see the gravitational field. It will give you a gravitational field, that. So the thing that the gravitational potential provides is that it will provide the gravitational potential per unit mass at any point. So what this means is that it appears to be it gives a more standardized value since everything is per unit mass rather than gravitational potential energy, which depends on the mass of the object. So it's much easier for you to visualize and compare the gravitational potential of bodies of masses because it appears to be more standardized. Alright, the next one is this particular equation. Now for this equation, you'll find it in the course book. So this equation, it might seem strange and it might be hard to even understand why this equation is here, but basically this equation is used to determine the velocity of the object, especially for objects in orbit. Alright, so we derive this from using the gravitational force and the centripetal force. So for the centripetal force, you should have learned it in chapter 1. Alright, so by doing by making them equivalent to each other and doing some algebraic manipulation, you just end up with this equation. Alright, so to be clear, this equation should only be used for objects that are in orbit, as I've written here. Alright, that's because we are equating the gravitational force and the centripetal force. Now, remember that centripetal force is a pseudo force. It's a pseudo force, which means that it is not its own force. It's a force that's provided by another force, in this case, the gravitational force. So since the centripetal force is provided by the gravitational force, we are able to equate them and derive this equation out, which can allow us to measure the velocity of the object and more. Alright, and now we'll go through the last equation. For the last equation, it's this particular equation. So hold on, Let me scroll up, take a look. I see, I did not copy the equation down. Let me just bring it down real quick. Yeah, so this is the equation that we are talking about. So for this equation, we can measure the time here. Time, the t here represents the period, which is the period of the orbit. And yeah, the point that this makes is that we are able to measure time rather than just distance and stuff like that. Alright, so for this one, we'll use this equation, which is from the previous chapter on circular motions, and we will equate it with the equation that we use above here. If you notice, it looks similar. Alright, but before that we square it first, because since this is squared, so we'll square them so that they can be mathematically equivalent. So by equating them and just doing some simple algebraic manipulation, we'll be able to create this equation, which can be used to measure the orbital period. Okay, so that's all for all of the 6 equations. And now we'll proceed on to the past year questions, just a few examples to help you get the hang of how the questions in the exams work. Alright, so now I'll go through some past year examples, just a few questions to help you get the hang of it. Alright, and we'll discuss only questions related to this chapter. So for now, we'll talk about Physics Paper 4, which is the 2018 version of the May-June paper, and it's the first version, take note of the one. Alright, so I'll skip question A, because question A is just a question asking about definitions on certain gravitational stuff that I don't remember what they asked, but you can just find the answer through your course book or through the internet. It's quite simple, right? So for this question, it asks that there's a distant star which is orbited by several planets. Each planet has a circular orbit with a different radius. Each planet orbits at constant speed. Explain whether the planets are in equilibrium. So this question, it borrows our knowledge from the last chapter in circular motion. Alright, so this is the distant star, and then imagine there's one planet here orbiting. Okay, so since it is in orbit, it is in circular motion. So is it in equilibrium? Well, we can determine by measuring or determining the velocity at certain instances. From here you can see that the velocity changes in the way that the direction changes. So since the velocity changes, then it is not in equilibrium. Okay, it is not in equilibrium. So what we'll write here will be, no, it is not in equilibrium because the velocity or acceleration, they can represent the same answer. Acceleration is changing. Alright, okay, so now we'll go on to the next question. So for the next question, we're given a table with the radius of the orbit and the orbital period squared of certain planets, and we're given a relationship here which says that r cubed is equal to kt squared. So the first question wants us to show that the constant k is given by this expression. Alright, so the first thing we can do is we can think, what can we find that is related to this question in general? Well, since we're talking about planets and we're talking about orbits, we know that we can use the concept behind the gravitational force and the centripetal force. That is, the gravitational force is equal to the centripetal force. Okay, so I've written it up here already, as you can see. So we'll just continue to write that down, and we'll try and see if we can find a way to make something similar to this expression over here. Alright, So first I'll remove the fractions, and I'll also at the same time I'll remove this 2m since they're both, you can cancel them out. So get something like this. Alright, so here we can remember that from our circular motion chapter, we learned that v is equal to r omega, where r is the, well, the radius, and omega is the angular velocity. Okay, so you can do it. So we should get something like, oh, hold on, we should get something like this. Alright, so upon expansion we'll get this. Okay, and here we know that the angular velocity is also equivalent to 2 pi over the period. Okay, so quite simple, we just substitute that in. For your information, this formula is also from your circular motion chapter, alright, which is the previous chapter. So by doing this, we'll get something like this. Right, so we expand this, and okay, here expand this, and we'll get something like this. 4 pi squared over t squared. Now if you notice, you should notice that there's a similar pattern between the relationship and the constant that we want. We can actually make it happen now. Okay, so now what I'll do is I'll try and make them look similar. Alright, so I'll multiply t square. Okay, so we'll get this, something like this, r cubed 4 pi square. And since r cubed is alone on one side, I'll try and make it such that r cubed is alone on one side. Okay, so t square, so I'll divide 4 pi square, so I'll get t square gm over 4 pi square is equal to r cubed. And voila, we have proved it. And k here, and this thing would be k. You'll notice that they look equivalent, this and this. Okay, so now we got question 1 down. So we move on to the second question. Okay, so for the second question, the question wants us to use the data from the table for the 3 planets and the expression for k to calculate the mass of the star. Alright, so now we have to calculate the mass of the star. Okay, we can just let me bring over the expression. Goes to k would be gm over 4 pi squared t squared. Okay, so to find the mass of the star, we can just substitute these inside easily, and we can find the answer. So let's see, we'll put planet C first. So for C, 9.6 times 10 to the power of 10 cubed equals to g times m. M is the thing that we're looking for, and g is the gravitational constant. So we can just leave it as it is first, and we can put in the answer later, the value later. So for t squared, it's 2.5 times 10 power 11. Now be wary of what they give you in the table. This is t squared already, so I have no need to square it again since it is already squared. The given value is already squared. Alright, so let's see. Okay, I'll bring out my calculator. And let's see, as we all know, the value for the gravitational constant is, let's scroll up and take a look, it should be 6.67 times 10 to the power of negative 11. Yeah, 6.67 times 10 to the power of negative 11 okay, so it should be something like 9.6. So m would be 9.6 times 10 to the power of 10 cubed multiplied by 4 pi squared divided by 2.5 times 10 to the power of 11 and multiplied by 6.67 times 10 to the power of 11. So this should give us a value of 4 pi squared 2.5 times 10 to the power of 11. 6.67 10 power of 11. Okay, this should give us a value of 2.09 times 10 to the power of 33 kilograms at 2 decimal places. Okay, now I'll not calculate the remaining ones, but do take note that for these type of questions you should always calculate at least 2 or more of the results. Now this is because we need to verify the answer. To further verify the answer, we should make more than one calculation to show that the answers are consistent. Because if we have so many values and we only use one value and we determine the mass to be this only, then it will be not wise to just base our answers off of one result. So always remember to calculate more than one of the answers if it's something similar to this type of question. Okay, now I'll not calculate this. I'll repeat, I'll not calculate this because it's going to yield a similar answer, but remember that you have to do so. Alright, so moving on to the next question, we're still doing May-June 2018, but we're taking the second version. Okay, so for the second version, state what is meant by a line of gravitational force. So above it says that a gravitational field may be represented by lines of gravitational force. So a line of gravitational force, well, let's think about it. Okay, so a line of gravitational force, oh, that's a bit too dark. A line of gravitational force, so imagine this, something like this. Okay, right, this would be lines of a gravitational force, right? So if something was in the line of gravitational force, what happened? Well, since you're in the line of the force, you would just be moved in the direction of that force, right? So the answer would be something along the lines of a line of force in which a test mass would be moved or an acceleration will be applied, or a force will be applied on a force. I think would in which a test mass would, I think it should be would have a force applied on. We have a force applied on, and the key is applied on in that direction. Alright, because we're talking about a line of gravitational force, so the gravitational force, the direction of the line will also matter, because maybe it could be going the opposite direction as well. Okay, so next, by reference to lines of gravitational force near to the surface of the Earth, explain why the gravitational field strength G close to the Earth's surface is approximately constant. Well, for this one, we can imagine Earth. Okay, so this Earth, I'll draw the similar thing again. Alright, now remember that these lines are representative of the gravitational field lines, and if we go if we zoom in, right, we will notice that the lines, right, like, so something like this, so Earth will be like this, so this is like the surface already, right? The lines will actually appear to be parallel to one another on the surface because of how big the Earth is. Okay, you might need to take some time to digest this, okay, but it's because the Earth is very big and the lines, they are radial, but if you zoom into if you zoom into the surface of the Earth, if you zoom into the surface of the Earth, which is already very, very small, it will appear parallel to each other. Alright, so for this, the answer would be something like, well, we should explain that the gravitational field strength would only be constant near the surface because in actuality, the gravitational field lines are radial, okay, and the Earth is very large, so we can say that the Earth has a large radius. It is very large. It's a large radius. So on the surface, the lines are parallel, or approximately, if you feel like it will give you a better sense of understanding. Alright, and well, since the gravitational field strength is determined by the gravitational lines, and since the gravitational lines are now equally spaced, gravitational lines are equally spaced, so the gravitational field strength is constant. Alright, okay, I hope you understand this. Okay, next. Okay, this is a calculation question. The moon may be considered to be a uniform sphere with a diameter of 3.4 times 10 to the power of 3 km and mass 7.4 times 10 to the power of 22 kilograms. Okay, the moon has no atmosphere. During a collision of the moon with a meteorite, a rock is thrown vertically up from the surface of the moon with a speed of 2.8 km per second. Assuming that the moon is isolated in space, determine whether the rock will travel into distant space or return to the moon's surface. Okay, so the key here would be determine if the rock will travel out into distant space or return to the moon's surface. Okay, so if you had trouble visualizing that, so now this is the moon. Okay, now a meteorite collided here, so something like that. A meteorite collided, and then now there is a small rock here that flew out. Okay, so now the rock flew out with a certain speed, which is 2.4 kilometers per second, and now we're thinking that whether or not the rock will just go in its own path and fly off, or if it will come back down to the moon, okay, by gravity. Now, how do we determine whether or not it will leave or come back? Well, for this one, we have to think with energy. We have to think in terms of energies, alright? So, in this case, well, it's quite simple, right? We've been given the speed. You can infer this from the information that you've been given. We've been given the diameter and the mass. Well, this is a very, very good formula for us to find the gravitational potential energy, right? Since it should be equal to negative gm m r. Okay, and well, since we're already given the velocity, then this means that we can find the kinetic energy of the rock, which is 1/2 mv squared. Okay, now notice that we are looking for the kinetic energy of the rock, so I'm using the smaller m here instead of the bigger m, because we're not looking for the kinetic energy of the moon. Alright, so to determine whether or not it will travel out, it's quite simple, right? So we can assume that if the gravitational potential energy is greater than the kinetic energy, then this means that the moon has enough energy to drag the rock back down to its surface. But if the kinetic energy of the rock is greater than the gravitational potential energy of the moon, this means that the rock will be able to escape. Okay, I think it sounds quite intuitive. Okay, so now we'll try and begin our calculation. So first, I'll calculate the gravitational potential energy. Technically, in this case, we can omit the symbol since we're just calculating the magnitude. So I'll just omit it for now. So 6.67 times 10 to the power negative 11 multiplied by m would be 7.4 times 10 to the power of 22. Alright, now here's another somewhat of a trick, okay? They've given you kilometers. Remember to convert it to meters because we need to use everything in standard units, SI units, okay? So 3.4 10 to the power 6. Okay, now this m would be the mass of the rock here. Okay, I'll leave it here as such first. And here we will get the answer to be, give me a while, I'm calculating it on my calculator. 3.4 times 10 to the power 6. We will get something, we will get 1.45 times, let me write that clearer. 1.45 times 10 to the power of 6 mass m joules. Okay, now let's calculate the kinetic energy. The kinetic energy will be 1/2 times the mass, which is m, which I'll leave as is, and the velocity, well, it's 2.8 kilometers per second. So what's that in meters per second? Well, we can just multiply that by 1000. So 2.8 multiplied by 1000, there will be 2800 meters per second squared. So this would give us a very nice answer of 3.92 times 10 to the power 6 mass joules. Now, this answer might seem confusing for some of you, but you can easily determine whether the rock will travel out into distance space or not, even with this answer, because we know that the m here that we're referring to are referring to the same rock. So this also means that the mass is unchanged. And it makes sense because even if we multiplied this inside or we took it out, it wouldn't matter, because if we multiply inside, it will just give the same value. They both will be multiplied by the same value. So the only different determining factor would be this number. Okay, so it's perfectly fine to omit the m. So obviously from here we can see that the kinetic energy is obviously larger than the gravitational potential energy. So 3.92 is greater than 1.45. Therefore, we can conclude that the kinetic energy is greater than the gravitational potential energy. So the rock will travel out into distance space. Okay, so that's all. And now we'll move on to the last question. Now the last question, I picked a slightly more confusing question that some students may feel to be a bit more difficult. Alright, so this one will be the May-June 2016 paper. It's paper 4 also as well, and it's the third version. Okay, so for this question, by reference to the first question, by reference to the definition of gravitational potential, explain why gravitational potential is a negative quantity. Well, this one is simple because we already explained it. It's somewhat similar to the explanation for the gravitational potential energy, where we set the infinity as a reference point of 0. Okay, we set as a reference point as 0, and well, the force of the gravitational force is attractive. Gravitational force is attractive. So which means that it's acting inwards. Force is attractive. So the work done as it is moved from infinity is active. There. Or you could write something like, or you could just say something like that, and then you can just say therefore the gravitational potential is negative. Okay, Because you can imagine like this is infinity, and obviously nothing can reach infinity. And then since the planet is here, the force is always attractive away from infinity. Okay, now we can imagine infinity like this kind of weird bubble thing that's like nothing can go past. So anything that goes in the opposite direction will be negative. Okay, so now we will talk about the next question. Two stars A and B have their surfaces separated by a distance, as you can see here, and then there's a graph here. Okay, there's a graph here. Okay, now you can look at the graph's curve and everything. All right, so the question is, a rock with a mass of 180 kilograms moves along the line joining the two centers of the stars from star A towards star B. So it moves like from star A to star B. Okay, so using the data from the graph, we need to calculate the change in kinetic energy of the rock when it moves from the point 0.1 times 10 to the power of 12 meters to the point where the distance is 1.2 times 10 to the power of 12 meters. And we need to state whether if it's an increase or a decrease. Okay, so from 0.1, you can see from here, you can just trace downwards and it will be here. Okay, so we can write that down so that it will make our life easier. At x equals to this one, then this will be equal to negative 10 times 10 to the power of 8. Okay, and at x equal to 1.2 times 10 power of 12, we'll just do a small trace, and we'll find that it's equal to 14. So negative 14 times 10 to the power of 8. Alright, so to find the change in kinetic energy of the rock, well, we can just calculate the energy. Now remember I told you that the gravitational potential is the gravitational potential energy per unit mass. Well, you can just assume that the energy is converted into kinetic energy, right? Because of the law of conservation of energy and stuff like that. So what we can do is first we can find the energy within the rock at each point. Okay, so for this one I'll call it as A and this one I'll call it as B. So at A, the energy, we just call it energy first, or we can just call it gravitational potential energy for simplicity's sake, would be negative 10 times 10 to the power of 8 times the mass, because it's the gravitational potential energy per unit mass, so it's something like E over m. So by multiplying the m, we'll get the energy. So quick calculation gives us negative 1.8 times 10 to the power of 11. Whereas for B, it will be negative 14 times 10 to the power of 8 times 180. So it will be negative 2.52 times 10 to the power of 11. Now to find whether if it's a change of, whether it's an increase or decrease, all we have to do is just to subtract from the initial value to the end value. Okay, so by doing so, we can just find that it will be 0.72 times 10 to the power of 11 joules. As you can see, the difference is positive, so this suggests that there will be an increase. It's that simple. Alright, so the last question here will be at a point where x is equal to 0.1 times 10 to the power of 12 meters, the speed of the rock is v. Determine the minimum speed v such that the rock reaches the point where x is equal to 1.2 times 10 to the power of 12 meters. So here we can look at it first. At a point where x is equal to 0.1, so this is 0.1, so here we need to determine the minimum speed such that the rock can reach here. Okay, I'll put a double star here. So how do we get it to reach that? Well, it's actually quite simple. As you can see, right, the gravitational potential will start to decrease, okay, decrease and then increase. Now remember why I said that it decreases, because we define the reference point 0 is at infinity. So which means that as you get closer to 0, the gravitational potential actually becomes weaker. Okay? And if you're wondering why there's a difference between the ends here, like why is this here and why is this here, it's because the stars, you can obviously see that they are different in size, which although doesn't directly say that there's difference in mass and there could be other factors, it gives you a sort of a hunch, a hunch that they have different masses. Okay, so the key here is that we just need to get this rock to be able to get to the top here, the highest point of this graph, the gravitational potential at the highest point of this graph. And after that, we can just let gravity do its work, and it will slowly be dragged into the other planets, into the other star. Okay, now this is something like an improvised version of a question of that one question that we did just now, the one that how can we get the rock to escape the moon without whether the rock will escape the moon or not. Well, it has to go past the gravitational potential energy, and you can see that at this point it's like the outermost regions of the gravitational potential energy of that star. Okay, I hope you all caught that. So now we'll find the top, the highest part of the graph, and find the gravitational potential at that part. So here we can see that it's at this point, so it should be negative 4.4. Alright, so we got it now. So phi is equal to negative 4.4 times 10 to the power of 8 times 10 to the power of 8, when it is at the point of, well, we don't need to bother ourselves with that, and we need the other one also. So this one I'll call phi 2. Phi 1 would be negative 10 times 10 to the power of 8. So what we can do is, we can of course do the same thing first. We can multiply by the mass to get the energy first. It will make everything less complicated. So it looks something like this, and then negative 10 times 10 to the power of 8 times 180, negative 1.8 times 10 to the power of 11. So now all we have to do is we have to find the difference between these two. Okay, because we already have these two are actually the gravitational potential energy already, if you caught up. Alright, so just by doing some subtractions, we can find that negative 1.8 times 10 to the power of 11 minus this 7.92 times 10 to the power of 10, it will give us, well, negative 1.008 times 10 to the power of 11. Now we have a negative symbol here, but it is fine to omit it because it doesn't really make a difference. Okay, now here we can just do the gravitational by the law of conservation of energy. You can just use this. 8 times 10 to the power 11 will be equal to the kinetic energy of the rock. So times the mass is 180 and the v squared is like that. So we should get that the velocity would be (3.3) times 10 to the power of 4 meter per second. And for this, this answer would be the velocity that we need, the minimum speed that we need, such that the rock can reach the point here. Okay, now I'll repeat again. The reason why we only need to bring the rock up to here is because this part, you can imagine that this part is like the part that belongs within the, this part is the region that belongs within the, this part, okay, this part belongs to the region within one of the stars. So basically what we're trying to do is we're trying to get the rock out of this star's gravitational field and into the other star's gravitational field. And the reason why we don't need to calculate the difference between this part and this part is because we're not trying, we're calculating the minimum speed, which means that we do not need to throw the rock directly towards the end of the star. Rather, we just need to help the star to help the rock to exit this star's gravitational field and enter the other star's gravitational field, so that it can slowly travel towards the star by being attracted to its gravitational field. And that is how we can find the answer. Okay. Now let's see if there's anything that I made that's not so accurate. Let me take a look. Hold on, I might have made a mistake. Oh yeah, I did make a mistake. We should, everything is the same, the answer will still be the same. The only thing is that I made my subtractions on the opposite side, in the way that we should, getting the negative is because we're not finding the, I assumed it differently. I thought that we had to find it from the difference between the first and the second, but we're just looking for this difference, so we should have taken the second part to subtract the first part. Now for this part, I should have said that we should omit it. We should have taken the second one and subtract by the first one. So this part should be wrong. In magnitude wise, for the values, they're all correct. It's just that I should have subtracted it like so. Okay, something like that. I'll just do it quickly, like this, and I will get 1.008 times 10 to the power of 11 joules. The thing behind this is that I just made my sequence of calculations incorrect, but overall the answers are still the same. So that should still help you with your understanding, because the difference, the only problem was that the difference that I calculated. You should take the second gravitational potential energy to subtract with the first gravitational potential energy to find the difference between them, to find what is the change. Alright, so yeah, that's about it for this chapter on gravitational fields. I hope that I didn't cause some confusion, because I realized that I made some mistakes. But if there are anything that you find confusing or that you find that you need help with, do feel free to leave a comment. I'll try my best to help you answer any of your concerns. And if you have any comments regarding the video, the audio, the editing, or anything like that, do feel free to comment as well, because I'll be happy to learn how to improve my teaching and my video recording skills. Yeah, so that's about it. Thank you.